Okay, you've got this piece of sheet metal that we're cutting squares of equal size from each corner, folding up the size to form this open top box. We're supposed to maximize the volume of the box. Okay, so I'm going to move this picture in here. And there's what the volume function looks like, because when you fold up the box, this X is the height of the box. 100 take away 2 of the X's from the corners of the square, or from the sides of the squares, is the width of the box. And here's the length of the box. And the domain of the function is X has to be between 0 and 50. If it's 0, you don't have a box, and if it's greater than equal to 50, you don't have a box either. So you can see that as I put values in this table here, it looks like as we get close to this number right here, we might be approaching a maximum volume. And here is actually the curve for the volume function. This blue graph is the graph of the first derivative of that function. And that derivative is equal to 0, 19.619, and that's where we're going to reach the high point on this graph right here. That's going to give us the maximum volume. The question is, how do you do that without a graph? Okay, well, here's your volume function. We can't reach a maximum volume at the endpoints of the function because the function is undefined there. So we want to find the critical numbers for this function. Where does the first derivative equal 0? And if I distribute this x, I get 100x minus 2x squared. I could multiply this all together and take the derivative term by term, or I could use the product rule, which is what I've shown here. So here's the first function times the derivative of the second, plus the second function times the derivative of the first, collecting or multiplying the factors together from each term and combining similar terms gives us this right here. And we want to know, when does that equal 0? I notice that every term is divisible by 4, so I make the numbers smaller by dividing every term by 4. So we've got this quadratic equation. If I pull this table up here and make it a little bit bigger, move that over there, you can see that I've got the quadratic formula here where the values of a, b, and c match the coefficients of the quadratic equation, and it looks like we have to eliminate the 63.714 because that's outside the domain. So it looks like squares of 19.6187 will give us the maximum volume. And there's an exact answer. If you use the quadratic formula but don't get a decimal approximation, 125 minus 25 radical 7 all over 3 is the value. And again, if you plug that number or this number into the original function, the maximum volume is about that right there. Okay, there you go. Hope that helped. If you have any questions, post a comment.